Today we'll start with one more project that is UART. Okay, UART, that is Universal Asynchronous Receiver and Transmitter. So actually, in the last class, I we discussed about ITC protocol. So protocol, there are two types are there. So my screen is visible, no? Just please respond. So my screen is visible. Shall I move forward?
Yes, sir, it is visible.
Yeah, yeah. Thank you. Okay. So there are actually two protocols are there. One is on-chip protocol. On-chip protocol means on-chip protocol means the bus, whatever the bus interface. If you want to communicate the peripherals within an IC, so let us take you have SOC, system on chip. Okay, in system on chip you have so many protocol, so many peripherals are there. So in order to communicate the peripherals present in the system on chip, so we are using what means AMBA protocols. Okay, we are using AMBA protocols. AMBA protocols means advanced microcontroller microcontroller bus architecture. Advanced microcontroller bus architecture. Okay, so this is the advanced microcontroller bus architecture. And next is yeah. So in this AMBA protocol, you will study about advanced high performance bus, advanced peripheral bus, advanced extended high performance bus, and wishbone. Okay, all these are what on-chip protocols. On-chip protocols means these are the communications within an IC. Okay, within a system on chip, that communication. Okay, and next you have off-chip protocols. Okay, so off-chip protocols means suppose if you want to communicate between the two ICs, two different last class we see in the I2C, that is master and slave, single master, multiple slave, multiple master, multiple slave. Okay, then you are going to study about serial peripheral interface (SPI). What is this SPI? Serial peripheral interface. Okay, SPI and UART. Okay, UART means universal asynchronous receiver and transmitter. Receiver and transmitter. And I2C we already seen. Okay, this is inter integrated circuit. Okay, inter IC inter integrated circuit. Okay, integrated circuit. Okay, IC inter IC integrated circuit. We discussed the I2C. Okay, so basically these peripheral, whatever the peripheral communication. Actually, this is serial communication. Serial communication, there are two types are there. One is synchronous communication. Another one is asynchronous communication. Synchronous communication and asynchronous communication. Synchronous communication means what? So whatever the data transmission happening, that is synchronous with the clock. Okay, that is clock will be there. So in synchronous communication, you have SPA, serial peripheral interface, and next one is UART, universal async. Sorry, you have I2C. Okay, you have SPI and I2C. Okay, so this is what synchronous type of communication. Okay, SPI and I2C. And next you have asynchronous communication, UART. UART means what? Universal asynchronous receiver and transmitter. Okay, so this is about the protocol we are going to develop. Okay, so today we'll discuss about is this fine the different types of communication protocols we have on chip and protocols and off chip protocols. Okay.
Yes, sir.
Okay, yeah. So actually, so if you take the asynchronous communication, so asynchronous communication means you have master and slave. For the master and slave, there is no clock between master and slave. That type of communication is asynchronous communication. When synchronous communication is there, means between the master and slave, there will be a clock. We are sending the data between the master and slave synchronous with the clock. Okay, so that is asynchronous communication. So what type of communication is there? Serial communication. Serial communication means what? You are sending, if you want to send 8 bit of data between the master and slave. So you will send one bit at a time. Okay. So one, suppose let us take, if you want to send 100 and 1010. Okay. So you will send one bit from the master to slave. Okay. That is serial type of communication. Okay. And normally like there is a, from the master there is parallel communication. Parallel communication means what? So from the master you are getting the parallel communication, like you will send 8 bits of data at a time. Okay, serial communication means you are sending one bit. Parallel communication means you are sending 8 bit of data at a time to the master. Okay, so in the digital also, like you have like parallel adder. So parallel adders, you are giving 4 bits of data to the full adders. Okay, and serial adders also we are seeing. Serial adders means you are taking one bit and you are adding to the serial adder. Okay, that also we discussed in the digital. So parallel communication means you are sending 8 bits of data at a time. Okay, that is parallel communication. And serial communication means you are sending one bit from master to slave. Okay, so there is no shared clock between the master and slave. Okay, so from the master, you are getting the signals through parallel. Okay, from the to the master. Okay, to the master from the other peripheral, you are getting the parallel data. Again, if you want to communicate between master and slave, so these are communicated serially. Okay, this is what type of communication? Serial communication. Okay, serial communication. And next UART. Okay, what is this UART? UART means what I told you: universal asynchronous receiver and transmitter. Universal asynchronous receiver and transmitter. Okay, UART stands for universal asynchronous receiver and transmitter. It's a hardware device. Okay, it's a hardware device used for serial communication. Okay, for what purpose it is using? Serial communication. Commonly found in microcontrollers, computers, and other electronic devices. Okay, other electronic devices. Okay, this is a one type of serial communication. So UART facilitates asynchronous communication between the devices by converting parallel data. Okay, parallel, whatever the parallel data coming from the computer or microcontroller into serial stream of data. Okay, serial stream that can be transmitted over the communication line. Okay, there are some communication lines are there. So RS-232. Okay, this is a fixed. This is a standard RS2 through RS-232 lines. You will send the RS-480 or 485 also. Okay, or TTL devices or vice versa. So RS-232 means, suppose here you have one microcontroller. Okay, let us take microcontroller. Here one more microcontroller is there. So if you want to communicate between these two microcontroller, so inbuilt there will be like one UART will be there. Okay, and here also one more UART will be there. Okay, so these two are communicated through what means through the line that is RS-232. RS-232 signal. Okay, so RS-232 means there are like we can call as null modem. Null modem is what? There are three lines are there. Transmitter is given to receiver of this signal, and here receiver is given to transmitter of this signal. Okay, again there is a common ground is there. Okay, this we call as a null model. Okay, so this is ground is common for these two. Okay, so normally like actually like UART, inside the UART there is TTL operated. Actually this is TTL operated, transistor logic. But RS-232 voltage levels are different. Actually TTL voltage levels are from suppose logic 0 means what? 0 means 0 volts means logic 0. Okay, actually 5 volts means logic 1. Okay, this is TTL operated. RS-232 voltage levels are different. Okay, RS-232 voltage levels are different. That is like it will be logic. That means so this is logic 0. So logic 0 will be from minus 3 to some minus 27, 29 volts, like this. Different voltage levels are there. So you need to convert one voltage level to, that is UART TTL to RS-232 voltage levels. So here inbuilt there is a max 232. So max 232 is acting like a conversion of the voltage level from TTL to RS-232 and RS-232 to TTL. Okay, this mostly you will study in the embedded, but our point of view is you need to develop this UART, universal asynchronous receiver and transmitter. Okay, is it fine? Shall I move forward?
Yes, sir.
Okay, yeah. So communication lines used in UART. I told you, no, RS-232 we are using. Okay, that is RS means what? Recommended standard 232. It is a standard for serial communication. Okay, transmission of data. It defines the electrical characteristics of signals, timing of signals, format of the data. RS-232 is commonly used for connecting serial devices. Okay, so whatever the serial devices, if you want to connect, like suppose here you have your computer or laptop. Okay, your computer or laptop. So these you can connect to, suppose you can connect to printer. Okay, and this one you can connect to scanner. Okay, or various devices. These are connected through the serial lines. Okay, for connecting the serial lines, we are using mostly this RS-232. RS-232 is recommended standard 232. RS-485 is the advanced version. Okay, so if you want to connect some modems, okay, if you want to connect some modems to this modems and printers, scanners, or various other peripheral devices to the computer, we are using this RS-232 232 lines. Okay, 232 bytes. Okay, these are serial type of communication. Okay, and um, so what is UART? That is universal asynchronous receiver and transmitter. That is a fundamental component in the digital communication system. This is the fundamental component in the digital communication system, enabling the serial communication between the electronic devices. If you want to communicate between the two different devices, so we are using this UART for serial communication. Okay, and so where we are using this UART, so uses, that means application of UART. If you take, okay, so users of UART, we can interfacing. We are using in the interfacing of peripheral devices, or we are using in the wireless communication. Okay, and control and monitoring system and industrial automation system. We are using this UART. Okay, so this is about RS. Uh, UART. Okay, this is UART, and see here, I told you, no. So that means there are two UARTs are there. So this is my master, this is my master, and this one is my slave. Okay, if you want to communicate between two UARTs, one master and one slave. So that means transmitter of slave is connected to the receiver of master, and transmitter of master is connected to receiver of slave, and common ground is there. Okay, here let us take this is ground. This is ground. Ground is common. So common ground is connected to master and slave. This type of communication we call as null model. This call as null model. So receiver of master is connected to transmitter of slave, and transmitter of master is connected to slave and common ground. Okay, this is one type of null model. Okay, and parallel to serial communication. Suppose if you want to convert parallel to serial communication, so in UART communication, data is transmitted serially over the communication lines, that is line wise, even though it's originally in parallel form on the controller bus. That means inside whatever the inside board. Okay, if you take a motherboard. Okay, a motherboard inside within this motherboard, what type of communication will be there? Parallel communication. That is a parallel communication. Okay, so that means if you want to communicate between the two means two peripherals, that means two microcontrollers or two computers or computer or a printer, then you need to convert this parallel form of data to the serial form. Why? Because these two can be communicated through the serial only. Serial communication. For serial communication, you are using RS-232. Okay, so the transmitting UART, so whatever the transmitting UART convert parallel data into serial data stream and sending it bit by bit on the receiving UART. Okay, so that means if you want to send 8 bits of data. Okay, suppose if you want to send 8 bits of data, so during the serial communication, it will send bit by bit, one bit, it will send. So that type of communication we call as serial communication. Okay, so next here there is a concept called baud rate. What is baud rate? Okay, there is one more thing, that is bit rate. Bit rate means what? Bit rate is actually number of bits transmitting per second. Okay, actually this is bit rate. Baud rate is actually number of like Yeah, this is same as number of signals transmitting per second or expressed as bits per second. Okay, bits per second. So this is a crucial parameter in serial communication. Okay, system like UART. Okay, so that means for UART, this is a crucial. So that means this shows the how much speed the data is transmitting, how much speed the data is transmitting. Similarly, in the modem also, when you are using internet, they will give your internet speed. Suppose they are giving like 100 mbps, okay, or 50 mbps. This is actually they are giving 200 mbps. They are giving the baud rate. Okay, how much speed the data is transmitting, how much of upload speed and download speed, they will specify. So that is nothing but a baud rate. Okay, they we call as baud rate. This is a actually this is a crucial part in the serial communication. Okay, so what it determines, it determines the rate at which data is transmitted between the transmitting and receiving devices over communication channel. Okay, so it will use the rate, that means how much speed the data is transmitting from between the transmitter and receiver, that is baud rate. Okay, there is a company called IBM given some particular baud rate for that baud rate standards we need to follow in the serial communication. So IBM company have given the fixed baud rates like 9600 or 4800. Okay, or 1 lakh 2000, like that fixed baud rates are there, that we'll discuss. Okay, so baud rate is what? That is number of, I told you, no, number of signals transmitting per second. That, or we can say that symbols transmitting per second. Number of symbols transmitting per second, or bits per second we can call. Okay, that is baud rate. Bit rate is what? Bit rate is baud rate only. So that is bits per second, number of bits per second. Baud rate is number of symbols transmitting per second. Okay, that is baud rate. Okay. So that means baud rate directly influences the speed of the data transmission. Okay. Higher the baud rate, if the baud rate is high, okay, if the baud rate is high, rate at which allows the faster data transfer rate, while lower the baud rate result in lower data. That means here the amount of data transmission, whatever the data transmission is there, that depends on the baud rate only. So if higher the baud rate, the data transmission is more. If lower the baud rate, the data transmission is slower. Okay, it's important to note that baud rate corresponds to rate at which the bits are transmitted, not the number of bits themselves. Okay, it's not the number of bits transmitting per second. It gives the rate, how much rate the bits are transmitted. That is what, that is baud rate. So I told you, no, number of it's a rate, number of signals transmitting per second. That is the baud rate. Okay. Um, so in asynchronous communication and asynchronous serial communication like UART, where there is no shade clock. Okay, shade, there is no clock. Why? Because the name itself it is there. So this is asynchronous. Asynchronous means what? It's a independent of clock. There is no clock. Okay, data will be transmitted independent of clock. Okay, there is no clock in this. Okay, so that means data will be shared between the transmitting and receiving devices. So that means this baud rate is served as a means of synchronization, for synchronization purpose. So mostly in the uh, synchronous communication like SPA and I2C. So this clock plays a major role for what purpose? For synchronization. Okay, for synchronization. In the I2C also we already seen. That means data will be transmitted when the clock will go from, during this clocks only. When clock is low only, data will be transmitted. Okay, that is used for the synchronous purpose. But here, the baud rate plays a major role for synchronization. Here there is no clock. Okay, so baud rate plays a major role for synchronization purpose. So that means both devices must operate at. So in order to communicate serial communication, so both devices should operate at same baud rate to ensure that data is transmitted between the transmitting and receiving end correctly. So you need to, like, in order to transmit the data between the transmitting and receiving end, so the both transmitting side and receiving side both should have same baud rate. Okay, both should have same baud rate for synchronization purpose. Okay, baud rate plays a major role. Okay, so what the transmitting device will do? Transmitting device will generate the bit stream based on its clock signal, while receiving device samples the incoming bits, okay, at the same rate using the internal clock, okay. So transmitting signal will transmit the bit stream, and receiving signal will sample the incoming bits, okay. And there are, I told you know, so the IBM company, they given a particular standard baud rate. So these are the baud rates. These are the baud rates. What are the baud rates? 1200, 1800, 4800, 9600. Actually, this is 9600 standard baud rate we are using. Okay, and so 19200 and 1,15,200. Okay, that means here 9600 means what? This much of bits per second you are transmitting the data. 9600 bits per second you are transmitting the data, okay. This is the actual baud rate, okay. So IBM company have given the fixed baud rates, okay. And bit time. So what is bit time? Amount or duration of the time allocated to single bit. Amount of duration of a time allocated to single bit, that is bit time, okay. So bit time equal to what? 1 by baud rate, or we can call as 1 by bit rate, okay. 1 by bit rate. So bit time equal to, so if you take this the 9600, so what is bit time? That is 1 by 9600 means you are getting 104.67 microseconds, okay. 10.674 seconds, okay. So this is the bit time. Actually, this is the bit time when you calculate. So you need to remember what is bit time means 1 by baud rate or 1 by bit rate, okay. This is the bit time, okay. And suppose if you calculate this bit time, if you take this one, which one? This one. If you take this value, that means 1,15,200 bits per second. So what is the bit time you are getting? 8.681 microseconds, like this you are getting the bit time, okay. So this is about the bit time. Bit time is a 1 by baud rate. It's the reciprocal of baud rate, that is bit time. So baud rate and bit time, how they are related? Baud rate is inversely proportional to bit time. This you need to remember. So baud rate, so whatever the baud rate is there, that is inversely proportional to bit time, okay. So baud rate is inversely proportional to bit time, okay. So number of cycles, so number of cycles equal to what? So that means time into frequency, okay. So if you take the reference clock as how much? 500 megahertz. For baud rate 9600, number of cycles required equal to how much? So that is bit time. What is the bit time? 1 by 9600 into, so this is bit time. The bit time into frequency. Okay, this is the formula for calculating the number of cycles. Okay, so number of cycles. So that means 1 by 9600 into my frequency. What is my reference clock frequency? 5000 megahertz. Okay, so that means if you calculate, you are getting 5 lakhs 20,833 clock cycles. These many cycles you will get. Okay, so these many cycles you need to generate for making this 9600 baud. Okay, is it fine? Do you understood any doubts or queries till now?
No, sir.
Okay, yeah. One second. Yeah. Yes. So this is about the number of cycles, that is time into frequency. Okay. Yeah. So next, so that means suppose number of cycles for 500 megahertz means how much? So initially we seen 5000 megahertz. Suppose if it is 500 megahertz with baud rate of 9600 means cycles equal to how much? Cycles equal to 50 megahertz by 9600 means how much you are getting? 5208 cycles. Okay, this is 5208 cycles we are getting. Okay, so this is actually for number of cycles for baud rate 50 megahertz frequency, and baud rate is how much? 9600. Okay, so 9600 means what? So that means here, so that means this is input. So from the input you are converting what from the input you are getting parallel data. So parallel data you are converting parallel to serial. Okay, parallel to serial, and this is actually what is this one? This is master, and this one is slave. Okay, so master and slave, you are sending the data from where to where, master to slave. So here this is tx, and here you have rx. Okay, so inside there will be a counter, inside there will be a counter, and there is a reference clock will be there. Okay, inside for the master there is a reference clock. So previously I told, the what is the reference clock for the 5000 megahertz, we already seen the number of cycles. Okay, and also for 50 megahertz reference clock we seen the number of cycles. So that means this is actually reference clock. Okay, so like this we need to communicate between the master and slave. Okay, so suppose 50 megahertz, 50 megahertz, baud rate 9600. So the number of cycle equal to how much? 5000, 5208 cycles. Okay, so within this 5208 cycles, one bit of data will be transmitted. Within this, that means what? For sending one bit of data, how many cycles are required? These many cycles are required. 5208 cycles are required. Okay. So like this, you are calculating the cycles. Okay. For sending how many bit of data? One bit of data. Okay. With a reference clock. What is my reference clock? Reference clock is 50 megahertz. Okay. 50 megahertz. Baud rate is 9600. So cycles, if you calculate number of cycles, if you calculate, you are getting how much? 5208 cycles. So these many cycles are required to send one bit of data. So 5208 cycles are required for sending how many bits of data? One bit of data. Okay. So one bit of data. So there is oversampling also. Oversampling means what? So for oversampling, how many cycles are required? That means cycles equal to 50 megahertz by 9600 into this 16 you need to divide. Okay, 16 you need to divide. So how much you are getting? 325 cycles you are getting. 325 cycles for oversampling. For oversampling, you are getting this many cycles you are getting. Okay, so here how you are sending means, first is start bit. Okay, you are sending start bit. This is how many bit? This is one bit. Start bit is one bit, and next data you are sending. Data can be how many bits? This can be 5 to 9 bits. Okay, so mostly you are sending how many bits of data? 8 bits of data. And parity bit. Okay, parity you came across like even parity and odd parity like that. This is also one bit. Okay, so so this can be 0 or 1. This is one bit, and one more is stop bit. Stop bit means what? This is also one bit. So you are making, so how you are sending means you are making a data frame. You are making a data frame with start bit, data, parity bit, and stop bit. Okay, this is actually data frame you are sending serially. Okay, so serially in the receiving also you are verifying with what the start bit and parity bit and stop bit. So both are verifying means, the correct signal is transmitted to receiver. Okay, so this is actually normally we call as data frame. Okay, you have start bit, that is one bit. Data bit can be 5 to 9 bits. Mostly we will prefer 8 bits of data. 8 bits of data means what? One byte. No, 8 bits of data equal to one byte. And parity bit can be either 0 or 1, and the next one is stop bit. Okay, you are sending 8 bit. This is a data frame. Okay, so that means if you want to send from the master to slave, so this is here this is transmitting and you are receiving. So you have start bit one bit, and you have 8 bits, and you have parity bit, and you have stop bit. Okay, so that means what is start bit? Did you understood how we are sending the data? Any doubts or queries till now?
Yes, I understood.
Okay, yeah. So start bit. What is start bit means? Your data transmission line is normally held at a high voltage level when it is not transmitting the data. So that means UART will be high voltage. Let us take 5 volts. It will be 5 volts when it is not transmitting. Okay, not transmitting the data. Okay, to start the transfer of data, the transmitting UART pull the transmission line from high to low. So to transmit, So it require how many cycle? Clock cycle, one clock cycle. Okay, it should pull the transmission line, whatever the transmission line from high to low. So the from it will pull from where to where, 1 to 0. Okay, high to low. So when the receiving UART detects the high to low voltage transmission, it begins reading the bits in the data frame at the frequency of that baud rate, whatever the baud rate you are giving. So that is 9600 if you take. So with this baud rate, it is going to receiving signal, going to read the bits. Okay, initially it will be high only. So that is it will be logic one only. It will be in the logic one. Okay, so when it starts transmitting, so it will go from high to low, and when it is going from high to low, receiver UR detects these signals. That is what high to low. So that is 1 to 0. It will detect in the voltage transition, and begins reading the bits in the data transmission at a frequency of whatever the baud rate is there. Okay, and start bit. Okay, what is start bit? So your data transmission line is normally held at a high voltage. Yeah, so this is same thing. Yeah, whatever I explained. So it will pull from high to low. Okay, and data frame. So I told you, know, data frame is how much? This can be 5 to 9 bits. Okay, data frame is 5 to 9 bits. So data frame contains whatever the actual data if you want to transfer. Okay. So actual data if you want to transfer, that is actually data frame. This is for 5 to 9 bits. Okay. So it can be 5 bits up to 8 bits. Okay. So mostly you will send 8 bits of data only. And along with parity bit is used. Okay. Parity bit means actually, yeah, there is a even parity and odd parity, odd parity, like that. Suppose here number of ones are there. Suppose 10, 10, 11, 00 is there. So this is the what? How many number of ones are there? 1, 2, 3, 4. So that means this is actually even parity. Even number of ones are there. So let us take, suppose let us take one more signal, 1110 and 1100 is there. So how many number of ones are there here? So 5 to 7 number of ones are there. That means odd parity. Okay. So like this, we can find out even parity and odd parity. Suppose if the data frame is 9 bits, parity bit is not there. There is no parity bit if data frame is how many bits? 9 bits. Most cases data is sent with LSB bit first. LSB bit first means what? Suppose if you take data bit is 1010 underscore 1100. Okay. So this is actually my LSB, and this one is actually my MSB, most significant bit. First LSB will send first, next bit. Like this it will send one bit. So mostly we'll prefer LSB, whatever the least significant bit will there, that will be sent first. We'll prefer that only. Okay. So this is about data frame. And parity bit I told you, know. Parity bit means what? Suppose here if you see, so 1011. 1011 means suppose if you are making with odd parity, so here odd parity you have three number of ones. That means parity bit becomes 1. Okay. And if here two number of ones are there, that means parity bit equal to what? 0. Okay. And stop bit means what? It should go from high to low. It should go from, sorry, low to high. It should go from where to where? Low to high. So start bit means what? Start bit when it start the communication. So initially when it is high, okay, when it is in 5 volts, there is no data transmission. It should go from where to where? 1 to 0. Then only the receiver will identify that this signal, and it will start receiving the data. Okay, this is start bit. And stop bit means same thing like this. In the I2C also we have start condition and stop condition. In start condition what happens? So first HDA will go from high to low. After that SCL will go from high to low. Okay, that is start condition. Okay, start condition. And what is stop condition? Stop condition means first SCL will go from low to high. After that HDA will go from low to high. Same like that. So here start condition. Start condition means it will go from high to low. Okay. And stop condition means again it will go from low to high. The same concept will come over here. So same like that I2C. There I2C you have two signals, HDA and SCL and HDA. There you have HDA and SCL. SCL and HDA. Here only one start bit and stop bit. Okay. So that means start bit should go from where to where? That is high to low. Okay, this should go from high to low to in order to start the communication. In order to send the data, it should go from high to low. And what is data bit? Data bit is 8 bits if you want to send. So mostly we'll prefer LSB bit will be sent parallel serially, and parity bit is optional. Suppose if you are taking 5 to 8 bits means parity bit will be there. Okay, parity bit will be there. If you are taking 9 bits means no parity bit. Okay, you are sending 9 bits means no parity bit. And stop bit means what? So vice versa. Start bit is going from high to low. So stop bit will go from where to where, low to high. So when it is go from low to high, it stops the communication. Okay. So these are the steps happening in the UART communication. First start bit, high to low, data 8 bit, parity bit is optional. Okay. If it is 5 to 8 bits, parity bit will be there. 9 bits, no parity bit. Stop bit means what? It will go from low to high. Okay. So this is the data transmission. Yeah, is it fine? Any doubts or queries?
No, sir, it is fine.
Yeah, thank you. Okay. Yeah. So here if you see the coding part, okay. So if you see the coding part, okay, coding I am writing. Yeah. This is for coding part. So if you see the coding part, so you have parallel to serial communication, and there is a baud rate generation. Okay, under the test bench, okay, under the top module, and there is a serial data. Okay, serial data. So it is transmitting to receiver, and it is sending serially, and again it is converting from serial data to parallel data. Okay, so this is the basic thing we need to do. Okay, baud rate generator also there. Okay, there is a baud rate generator will be there. So we need to write the code for transmitter, receiver, as well as baud rate generator also we need to write. Okay. So what is first we'll see baud rate generator. What is baud rate generator? So baud rate generator means what? Baud rate generator have the clock that is 50 megahertz. So that is 9600. So baud rate generator, and have receive enable and transmit enable. Okay, receive enable and transmit enable. So how we are generating the baud rate? So previously we already seen. Suppose baud rate is 9600 and frequency is 50 megahertz. You need to calculate the bit rate, no? So you need to calculate the that means bit rate cycles, number of cycles. Number of cycles equal to how much? So 5208 you got. Okay. So that means counter. You need to develop a counter such a way that it should count from 5208 to 0. That is given to transmit enable to send one bit of data. To send one bit of data, this many cycles are required. Okay, this many cycles are required to send how many bits of data? One bit of data. Okay, so that for that you need to develop a counter for the baud rate generator. Okay, so see here baud rate generator. So 50 megahertz baud rate, receive enable.
Is
That
it,
is
sorry, sir.
yeah, yeah. Tell me.
So is it those many cycles for one bit or for 9600 bits?
One bit, one bit. This is actually baud rate.
Okay.
For sending one bit of data, this many cycles are required.
Yeah, yeah. Okay, okay.
Okay, this
Understood.
many cycles are required. Yeah. So next you have transmitter also. So transmitter also you can form an that means baud rate equal to 9600. Frequency is 50 megahertz. So this is actually number of cycles. You need to develop a counter for 5000. This is number of cycles. Okay, number of cycles. So number of these many cycles are required. That means for this you need to develop a counter for transmit enable also. Transmit enable. So 5208 to 0. Okay. So you need to develop a counter. So uh, yeah. So one second. So counter receiving actually it will start from 325 to 0. Why? Because we have oversampling. No, for oversampling, you are getting number of cycles equal to 325. Okay, 325 to 0. This is for receive enable, and for transmit and counter receive enable also you need to for transmit enable you need to generate that much of counter 5208. But for receive enable, due to oversampling, you need to develop a counter, that is receive counter receiver, that is from 325 to 0 counter you need to develop. Okay, so transmit enable is for transmitting, and receive enable is for receiving. Receive enable is for receiving. Okay, so that means here actually like for counter transmit enable, this many cycles are required, and the counter receive this many cycles are required. So that means you need to calculate the mod of a counter. Okay, so how to calculate mod of a counter? So that means mod, if you take mod n, there is a formula. So the n is less than or equal to 2 power n. Okay, so 2 power n. So that means n is less than or equal to 5208 means, if you want to represent this one in terms of 2 power, so this means this is equal to what? This is actually 2 power 13. Okay, 2 power 13 means 13 bits are required. 13 bits are required. This many bits are required. 13 bits. Okay, these are nothing but number of bits. Number of bits. Okay, actually number of bits. Okay, we'll see in the counters also. Counters we discussed how to find out the number of flip flops, or suppose 3-bit counter is there, so it will count 3 bits. That means 3 number of flip flops are required. That means you need to declare the n equal to what? 3. So this is mod 8 counter. Okay, so actually this is mod value. Actually this is mod value. Okay, and next 325, if you take 325 is less than or equal to 2 power n means, if you want to declare 325 means mostly 10 bits are required. Okay, mostly 10 bits are required for 325. Okay, so this is about baud rate generation. So we'll see the code for baud rate generation and we'll come back. I'll open the code for baud rate generation. One second. So this is baud rate generation. Okay, so baud rate generation here. So normally, what you need to do, you need to develop a counter. Okay, so module baud rate generator, input clock, output transmit enable, receive enable. So transmit counter is how many bits? 13 bits. That means reg I need to declare 12 down to 0. This is 13 bit. Receive counter is how many bits? 10 bits. That is receive counter. That is 9 down to 0. Receive counter. Always at the rate passage of clock. Begin. If transmit counter equal to 5208, transmit counter equal to what? 0. Else, else what happens? It should count. It should count from where? That value. So transmit counter equal to transmit counter plus 1 tick binary 1. Okay. So end. So like this, I'm generating, means I am developing the counter for transmit transmit counter. Okay. This is receive counter. Always at the rate passage of clock. Begin. If receive counter equal to 325, receive counter equal to what? 0. Otherwise, receive counter equal to what? Receive counter equal to receive counter plus 1 tick binary 1. Okay, so that means every when counter reaches 5208, transmit enable will be activated. So transmit enable is activated means what? One bit of data is transmitted from transmitter to receiver. Okay, similarly when receive enable is that means when receive counter reaches 325, then receive enable will be activated. When receive enable is activated, so one bit of data is received from transmitter to receiver. So I am using continuous assignment statement. The same transmit enable equal to transmit counter, that is equal to 0. So then I am using ternary operator. If condition is true, then 1. Otherwise 0. Okay. And assign receive enable, that is receive counter equal to 0. 1 tick binary 1. And if it is condition is satisfied, then it is 1 tick binary 1. Otherwise 1 tick binary 0 and end module. Okay. So this is the code for what? This is the code for baud rate generator. Is it fine? Any doubts or queries till here?
No, sir, it is fine.
Okay. Yeah. So just open the Vivado. So go to file, project, new project, next, and what is my project name? UART. Okay, UART, and go to the folder. Uh, so here is my folder. Training and development. Training and development, and my, and in this uh, we can batch, yeah, we can batch RTL codes using GVim. Next, next, and I need to create my file name. Let us take what is my file name, module name. Okay, let us take border generator. Okay, this is my border generator. Copy this and create, choose the location. Okay, UART, UART. One second. Yeah, value given. Okay, yeah. One second. Here, this path I need to select. Next, next, create, choose the location. UART, select. Okay, next, next. This is optional. Okay, next, finish. Okay, yes. Yeah, this is border generator. So here I'm just select all, copy this code, and here you paste. Okay, save this file. Okay, this is the border generator. Okay, and next coming to this yeah. So coming to next part, this is border generator, and next is write operation. So write operation, if you take, so that write operation is happening from the transmitter. Okay, so what are the inputs for this? You have clock, write enable, and one more enable is there, reset, and data underscore 8. Data underscore in is 8 bits. Okay, and transmit signal is there, that is the serial data. Serial data, one more busy flag is there. So when busy equal to 1, then UART is said to be busy. When busy equal to 0, then UART is said to be idle. Okay, this is write operation. And here so that means we need to develop a state diagram such a for the write operation. First it will be in idle state. Okay, and when write, so first write, when write operation will start, so write enable should be 1. Okay, write enable should be 1. We already seen in the previous projects, no, that means in the RAM also, RAM and FIFO, when write enable equal to 1, then write enable equal to 1, then it will start the write operation, no. So here also it should be 1. Write enable equal to 1. It will go to the start state. Okay, and in the start state, clock enable equal to 1. Okay, and clock enable equal to 1, and it will go to next state. What is the next state? Data, and here clock enable equal to 1, and counter will be initialized to 7, and next it will come to the stop condition, and again clock enable equal to 1 means again it will come to the ideal state. Okay, so this is normally my write operation. Okay, uh, next so if you see the code, this is transmitter. Okay, so we need to initialize. So module transmitter, input clock, write enable, input reset, input enable. How many bits of data? 8 bits of data. Input 7 down to 0, data in, and output reg tx and output busy flag. So I need to declare how many states are there. Total 4 states are there. Okay. So we have 4 states now. So these are 4 states. So 4 states means we need to declare the states. Okay. So that means here so I'm declaring a parameter. What is my ideal state? Ideal state equal to 2 tick binary 0 0. Parameter start state is 2 tick binary 0 1. Parameter data state equal to 2 tick binary 1 0. Parameter stop state equal to 2 tick binary 1 1. Okay. I'm declaring some intermediate variables. Those are with reg data type. Reg 7 down to 0 data. Reg 2 down to 0. 7 down to 0 data means 8 bits. Reg 2 down to 0 index. This is 3 bits. Reg 1 down to 0 state. Okay, I'm declaring some intermediate states and intermediate variables with reg data type. And first I want to write the reset logic. How to write the reset logic? Always at the rate passage of clock. If reset equal to 1, begin. So when power on reset, transmitter should be 1, no. So it should, when it starts transmitting, it should go from high to low. Okay, and what is the state? It will be in idle state. Index is 0, and data is also 0. Okay, this is the reset condition. Else begin case state. Okay, case state. So state So that is idle state. Okay. So what is idle state? So idle state begin if write enable. If write enable equal to 1. Okay. Idle state if write enable equal to 1. Where it should go? State equal to start state. It should go to the start state, and whatever the 8 bits of data is there, that will be given to the data, and index equal to what? 3 tick binary 0. Okay, this is actually idle state. I wrote for idle state. Okay, so this is my idle state. And next, coming to the start state. The start state begin. In the start state, what I am checking? I am checking for the enable. Okay, clock enable. Okay, so I am checking for the clock enable. So that means if enable, so I need to make the start bit. So how to make the start bit? So initially in the idle state, transmission is 1. In the power on reset, transmission bit is 1. So I need to pull this transmission from 1 to 0, high to low. So this is the start bit. Okay. And what is the state? That means the next state equal to what? Data state. Okay. Next state equal to data state. This is actually I starting the condition. This is for start condition. I need to pull the transmission transmitted signal from high to low. Okay. And next is data state. Okay. So data state, in the data state, what will be there? So this is my data state. So counter will be 7 and clock enable equal to 1. Okay. So if you see this data state, this is my data state. Okay. The generator I will close. Okay. So data state begin if enable equal to be enable, transmit equal to data index if index equal to 3 tick h7, and what is the state? That means 8 bits of data that should be sent in the data state. Okay. So what happens? It will go to the next state. What is the next state? Stop state. Else index equal to what? You need to add index. Okay. Index will start from 0, 0, 1, 2, 7, up to 7. 8 bits of data. You are so for 8 bits of data you are sending with index. Okay. Data index. Whatever the data of index is there, that is sending to the transmit pin. Okay. Through the transmit pin. And this is data state. And what is the next state? Stop state. Okay. If all 8 bits are completed, then it will go to the next state, stop state. In the stop state, what happens if enable transmission equal to 1 tick binary 1? So it should pull from where to where? That means from low to high in the stop state. And what is the next state? It should go to the idle state. What is the next state? It should go to the idle state. Okay. So it should go to the idle state. And what is the default state? Begin for case statement, there is a default statement. Okay. So why? Because if default statement is not there, we discussed in the test bench for default D flip flop, it will infer as a latch. Okay. So that you should need to remember. For case statement, you should have the default statement. So Tx equal to 1 tick binary. So this would be 1. And what is the default state? Idle state. Okay. End case, end, and I need to assign BC equal to what? That is state not equal to idle state. So when it is in, I told you, no, like when it is in idle state, so what happens? Busy equal to 0. Either it may be start state, data state, or stop state. Busy equal to what? 1. Okay. So I am checking that condition. That is assign. I am using a continuous assignment statement to assign. Okay. Busy equal to state not equal to idle state. So when it is not there in idle state, then it is busy. Okay. Other than that idle state, remaining states it is busy. Okay. So this is the transmitter transmitter code. Did you understood any doubts or queries?
No, sir, it is okay.
Okay. Yeah. So here what I need to do. So just copy this and go to the design, add the design source, create and choose the location, UART, select, okay, and finish. Okay. Yes. Okay. This is my transmitter signal. Okay. This I need to save. Yeah. So select all, copy, and here you need to paste and save. Okay. This is a transmitter signal. And next coming to the receiving part. Okay. UART receiving part. So what is UART receiving part? Receiver should read the operation. For reading, for receiver also you have clock reset, and you have ready clear. You have ready clear and clock enable, and receiver. This is serial input. You are receiving 8 bits of data, one bit LSB first, and next one is ready and data out. Data out is 8 bits of data. Okay, 8 bits of data. So here, yeah. So here if you see, so for receiving, what you need to do, you have start bit, data out, and stop bit. So how many samples are there? 4-bit samples. Index is 4-bit, and you are declaring with temp with 8 bits. Okay. So here what happens means there is a timing diagram. Transmit enable becomes what? 1. Okay. Transmit enable equal to 1 means every time receive enable after how many cycles means 1 2 3 4 5 6, like 6 cycles, it becomes transmit and receive enable becomes 1. Okay. Receive enable becomes 1, and so start, it will start the data, and so every time after sending that 325 bits, 325 cycles, data bit will be one data bit will be received. Okay. So this is the timing diagram. Okay. So that means there is a oversampling. Oversampling is how much? 16. Okay. So that is from 0 to 16. So start bit, when it is going from start bit, so receive should be 0 and sample is not equal to 0. Okay. And next, like this, it is sending 1 to up to 15. After 15 again, so after 15, so sample becomes 16. So index becomes 8, and it will come to stop. Again sample becomes 15, again it will come to the start. Okay. So for this I need to write the code. Okay. So you have a timing diagram for receiving bits. Okay. So for this I'm writing the receiving signal. That is this is UART receiver. UART receiver. So UART receiver, input clock, input reset, input receiver, ready clear, input clock enable, input reg ready, and data out is 7 bits. I need to declare how many states are there. Total 3 states are there. Okay. So I need to declare this 3 states. Okay. So if you take the 3 states, parameter start state is 2 tick binary 00, parameter data out state is 2 tick binary 01, parameter stop state is 2 tick binary 10. You need to declare the internal variables. What are the internal variables? State, that is a 2 bit 1 down to 0, sample 4 bits 3 down to 0, index is 3 bits 2 down to 0, temp register also 8 bits. Okay. And first you need to write the reset logic. Okay. What is the reset logic? Always iterate passage of clock begin if reset ready equal to 0, data out is 0, and what is the start state? What is the initial state? Start state, no? So initial state is what? Start state. Sample is 0, index is 0, and temperature is 0. Else begin if ready clear. Okay, if ready clear, you see in this one, yeah. So this one, it is going to the next state, no? Yeah, next state. So when ready underscore clear equal to 0, ready equal to 0. If clock enable case state. Okay. So start state. So start state receive equal to 0, begin sample equal to sample plus 1 tick binary 1, and you are checking for sample for 15. Okay. So it should sample from 0 to 16. That means you are checking for where sample equal to 15. So till this condition is satisfying, data state. So what is the next state? Next state equal to data underscore out state. Sample becomes 0, index 0, and temperature becomes 0. If condition is not satisfying, okay, what happens? Sample will be incremented. So sample will be sample plus 1 tick binary 1. Okay. So normally this is start state. And next data state. So in the data state, what we did, sample equal to 15 and index equal to 8, I need to check. Okay. So in the data state, data output state begin sample equal to 1 tick binary sample plus 1 tick binary 1. If sample equal to 4 tick H8, then temp register index equal to what? Whatever the data present in the receiver, that will be coming in the temp register. Okay. And every time you need to increment the index. Okay. and end, you need to check for two conditions. What are the conditions? Sample equal to 15 and index equal to 8. Okay. So that means if index equal to 3 tick decimal 8 or sample equal to 4 tick HS, what is the next state? It should go to the next state, stop state. Okay. So this is my data state. And coming to the stop state, in the stop state, what we have seen, so sample equal to 15. Okay. So that means sample equal to sample plus 1 tick binary 1. And if sample equal to 15 begin, what is the next state? That is, it should go to the start state, and whatever the data present in the temp register, that it should be coming into, you are reading the data. Okay. That should come into the data underscore out, and ready becomes 1 and sample equal to 0, end. What is the default state? That is start state only. Okay. So this is my receiver signal. So here
So what is the use of this ready signal?
ready signal, actually it is checking for so in this timing diagram. So in this so actually, like if ready clear equal to 0, here I am checking ready signal equal to 0 only. So that means it is checking like a busy flag only. In the transmitter, we see in the busy flag, no? So
Yeah.
like that in the receiving, I am checking for the ready signal. So when it is there in any of this data state, stop state, so then ready signal becomes 1. Okay. Ready
Mhm.
signal becomes 1. Okay. Yeah, that is ready signal. In the stop state also, I am checking for ready signal becomes 1. Like that I am checking. And next, this is your top module. This one I will add. One second. This is receiver, no? So this is receiver, and I'm adding the design source, create receiver to the location, toward select, okay, and finish. Okay, yes. So UART receiver. Um, so this code select all, copy, and here you paste. Okay, and one more. This is receiver is over. Receiver is over. Okay, and next is top module. Top module. This is my top module. So select. So here module you are top. So input reset and input 8 bits, write enable, clock, ready clear, ready, busy, and 7 down to 0 data out. Okay. I need to declare the internal variables. Okay. Wire receive clock enable, wire transmit clock enable, and wire transmit temp. Okay. So in the top module, what I am doing, I wrote the code for baud rate generator, and I wrote the code for transmitter. I wrote the code for receiver. I need to instantiate that design in my top module. How to instantiate? What is my so baud rate generator? If you take, what is my design name? Baud rate generator, and what is my instance name? BG, and this is by connection by name. Okay, and here also transmitter also I need to instantiate transmitter. Transmitter is my design name, and US is my instance name, and this is connection by name. And UART receiver also. UART receiver is my design name. UR is my instance name, and this is connection by name. Okay. So I need to write this top module also. Okay. So just copy this module, copy, and design source. Go to the location. UART select. Okay. Finish. Okay. Yes. Select all, copy, and your top, Here I will paste. So my under UART top, whatever these are there, those are instantiated. Okay. I think I wrote this code. One second, I will show you. Uh, so what project? I'm opening this. Yeah, TB also I wrote. Okay, this is my test bench file. How to write TB for the top module? I wrote the TB. Okay, so that means here if you see the TB file, so you are the top underscore TB for top module. I'm writing the test bench. So clock reset data in write enable ready clear ready busy D out. I need to so these I need to declare with rich data type and ready busy D out I need to declare with white data type. I need to instantiate. Okay. So that means so you are top UUT. This is my instance name and whatever the variables outside the bracket are design inputs and outputs. Inside the bracket are the test bench inputs and input test bench variables. Okay, this is connection by name, and you need to generate the clock. Always hash by clock equal to not of clock with 100 megahertz, and you need to initialize the reg variables. Okay, initial begin clock equal to 0, reset equal to 1, write enable equal to 0, ready clear equal to 0, data in equal to 8 tick 0, 8 tick h 0 0. Okay, I told you the task functions and tasks. No, so function task here I can write the I can give the stimulus. That means I can write a task based test bench. I can use here task based test bench. Okay. So this is what I'm writing the task. Task send byte input 7 down to 0 D in begin. Okay. We already discussed with one example with D flip flop when I explain the functions and tasks. Okay. Wait equal to not of busy at the rate negate of clock data in equal to D in write enable equal to 1 at the rate negate of clock write enable equal to 0. Okay, this I wrote for the send byte task for send byte task for clear ready. So begin at the rate negate of clock clear ready clear equal to 1 at the rate negate of clock ready clear equal to 0. Okay, and I am giving the stimulus. Okay, initial begin repeat for 5 times. Okay, repeat for 5 times at the rate negate of clock I am applying reset equal to 1. Suppose if I want to send A, okay, normally if I want to send A, so A, capital A in the ASCII, what is that value? 41, 7 bits of data. Okay, normally I am sending 8 bits of data, padding with normally with a 0, the value will not change. No. So first I am calling the task. What is the task? First wait task. Okay, so I wrote for ready clear. Wait busy, transmitter starts, wait not be the transmission finished. Okay, wait ready. Okay, wait ready. Okay, wait ready and dollar display. So I want to display that. So clear ready. And if I want to send V also, this is the ASCII code. First wait busy. Okay, transmission started. Wait not busy, transmitter finished. Wait ready. Okay, I want to give the ready for receiving and clear. I need to clear. I need to run for 500 time minutes. Dollar finish means finish the simulation. Okay, so I wrote the task for send byte and clear ready also I wrote the task. Okay, so this is my test bench code, and so what I need to do, so this is my top module. Here I wrote the code for baud rate generator, transmitter and UART receiver. Okay, so run simulation, run behavioral simulation. You are getting errors. getting errors in this. 23. So like this, we need to write the code for UART receiver. Okay. So these outputs I will share you.